Hello and welcome to the course on electromagnetic theory. In this set of lectures, I will cover all the basics of EMT as well as very standard questions. So this is intended for um, GATE and other competitive exams. So like GATE or EE or EC, instrumentation and physics. So in this, I will cover all the basics which you need to understand the concepts as well as will be solving very standard questions. So the questions will be of gate type like NEAT and MCQ as well as MSQ, multiple select. So by solving these problems, you will be familiar to go into the exam. So you will be given a standard questions which you can solve by pausing the video and then you may review your solution. So we will be doing. So these lectures are designed with thorough revision, so that every concept is covered, and also you will get everything needed to be prepared for the exam. So, so I will start with in this lecture. In this lecture I will be starting with vector calculus. So they will understand the all the basics and everything that is needed for EMT from vector calculus. So you will not be facing any issue while solving the problems. Essentially, EMT problems that come in GATE exam, there are two things that are required for solving the problem. Firstly, mathematics. Initially, we have to put some time and effort to understand the mathematics. Once we understand that set of mathematics, which is not so much, it is just a small amount of things that we have to know in mathematics, but we have to be very clear with each of that. Plus, concepts of EMT. We have to be clear with all the concepts of EMT based on whatever the syllabus is for your GATE paper. So, in this way, you can um, easily solve the questions. So, now I will start with vector basics of vectors. So it's like in this, I will cover everything that is required for EMT. So firstly, like we have scalars and vectors, and scalars have magnitude but not direction. Like voltage is a scalar, temperature is a scalar, pressure is a scalar, density is a scalar, so on. Whereas vectors has both direction and magnitude, like electric field, gravitation field, magnetic field, and so on. So both scalars and vectors, uh, they both depend on time and position. For example, if there is a when we take an example of scalar, so we are considering an area here. in the space, in the 3D space. Now, if we take temperature at this point, particular point A, and there is also another point B. Now, if we take temperature at TA and also TB, these won't be, I mean, this is most probably it could be different. It is likely to be different because the uh, temperature depends on the position in space. Temperature depends on position in space. Now, TA, if we measure at t is equal to 0, then after sometimes suppose if we measure at 10 seconds, it varies. So the thing is that uh, the scalars, whichever it is there, it just keeps on varying. So, like not every scalar varies, but some scalars, whichever like temperature or pressure, also will follow the same time. So here these are called fields. So it can be called as a scalar field. Hence, temperature and pressure are scalar field. You can also check for other scalars whether they can be considered field or not. If they can vary with position or time or both position and time, then it is called field. So yeah, and the similarly, if we take vectors like electric, we call electric field. Why we say this as electric field? Because it varies with position and time. It can vary. I'm not saying it must vary, but it can vary. So that's why we call it as a field, and we write as a function of time and also the position. So that's why also we call gravitation field or magnetic field. So essentially, I mean to also whenever you hear field, you must get the notion of this variation with space and time. Now the next thing is okay, next thing that is important is differential length. It is denoted by dl. So I mean we can put small l instead. Um, Take a parallelepiped like this. Imagine that they are straight. So basically, two parallelograms are connected like this. So basically, it's a parallelepiped. Now, this is used to define the differential length, differential area, and differential volume. So, in this is in 3D space. So, I am using Cartesian coordinates, and this point, let's say this is A. A is at XYZ, and this length. So this is x-axis and this is y-axis, z-axis. So whenever we are putting XYZ axis, we have to follow the convention of right hand rule. That is when we are moving from X to Y. For example, we are rotating some screw from X to Y. It will move towards Z direction. Basically, it comes out of the table when we do that. So that is Z direction, and we have XY here. Let's consider that this length is dy and this length is dx and this is dz. So basically this point is, let's say it is B, and let's say this point is C. Now the dl is nothing but magnitude of dl is nothing but distance between B and C. So it is the diagonal of the parallelepiped. Um, so what is the B coordinate? B coordinate, it is only changing in x direction because it is x-axis. So it is B is x plus dx comma y comma z. Now how about point C? It is so in this direction we have got dy and yes, we have got in this direction dy, and so C is nothing but it is x comma in the y direction it is y plus dy comma z plus dz. So now magnitude of dl is nothing but distance between these. So when we do that, distance between B and C is x2 minus x1 whole square, x plus dx minus x whole square. So it is dx whole square plus um, y and y plus dy. So that will be dy whole square and it is dz whole square. So this is the magnitude of differential length here. Now the vector dl is nothing but dx x cap plus dy y cap plus dz z cap. This is the differential length, and it has um, like you will as we go along you will understand how it is implied and how it is used for solving the problems. Similarly, we have next. Let's see differential surface. So for the same parallelepiped like this, so we know that each side is, so this is dy and this is dx and this is dz. So here surface area of this is dx dy. Similarly, here also it is dx dy, and this one is so this one what it is dx dz. So yeah, so differential surface ds can be dx dy based on which side we are considering, or dy dz, or I should not write like this. Should let me ds equal to dx dy, and ds is equal to dy dz based on which side we are considering, or it is dx dz. Now the direction here, direction is always perpendicular to uh, the plane of that surface. So here if we consider the xy, then the perpendicular direction is z. So basically these are magnitude. Now we have to write vector which has both direction and um, magnitude. So this is z cap. If it is along or dx dz y cap, can be also it can be also minus z cap. So we just have to see, we have to check which side the normal vector is there, or it can be dy dz x cap. Now differential volume is nothing but dx dy dz. This is the volume of the parallelepiped. Now let's focus on the dot product of two vectors. Suppose we have a two vectors, a bar is equal to ax cap, or you can put I cap here, whichever you prefer. Ax x cap, ay cap, plus az z cap, and there is another vector b bar. So let's say the vectors are like this: a bar. So what does dot product implies is it implies magnitude of a multiplied with magnitude of b along the direction of vector a. So basically, if there is theta, then along a, this vector b has a uh, magnitude of b cos theta. So it will be like um, magnitude of a, and the magnitude of b cos theta is the component along. Basically, this means magnitude of b along a direction, a bar direction. Magnitude of vector b bar along a bar direction. So product of these two implies the dot product. So let's take an example like work done. To calculate work done, we do the dot product of force and displacement vector. So let's say we have a stone here and it is moved. So let's say this is the center of mass and this is the displacement vector. We have to consider displacement vector only. Um, it is moved in this direction from this position A, position 1 to position 2. So P dot product like this force times, sorry, not ds, it is now let's consider an example of work done. So work done is the dot product of force and displacement vector. um, let's say let's write displacement vector with some also here for dot s bar. So let's consider a stone and it is moved to this point. So size is same. This is center of mass. The same stone. It is moved along this path, straight line from position 1 to position 2, and this is the displacement vector. So dot products will give the work done. Now, what if the stone is moved from 1 to 2 along a path like this? Something. Firstly, it is moved like this here, and then it is brought here, and ultimately, I'm just tracing out the center of mass position. So the stone is moved such that the center of mass of the stone move like this, and it comes to here. Um, Now, in order to calculate the work done here, we have to bar dot ds bar. So what is ds here? Ds is the small element like from here to here initially. Now we are calculating this motion, this displacement ds bar times the force dot product, uh, and then we are integrating all along the path. Let's name the path P. Now these two equations are very important for you. Please keep these two equations in mind because this will become very important while solving the problems. Understanding this difference is very crucial. So have the sense of mathematics all the time while learning EMT because it is crucial for understanding and also solving the problems. Now in this case, we have seen so how we are calculating work done. Maybe we will calculate other things in EMT, but just to differentiate how we are calculating work done in two cases, I am showing this. Here we have displacement vector and also force is a vector as we know. So the same force is up. I mean the force is applied um, in different ways. Uh, so that's why we get two different paths. So this is P1 and this path is P2. So in path P1, as it is, the path is continuously, the direction of the path is continuously varied here. So we have considered the ds uh, displacement vector ds here, and then we did integration, which comes in the second case. So this will be applied for path P1 case, and this is applied to. Now in EMT, there may not be two possibilities of some displacement or um, some, but either of the case can be there. Either this might be applied or this might be applied, but we need to understand uh, why we are using this formula or this formula. That's thing about this. Now, similarly, I can also give another example. Now, let's take the surface. Yes. So, area of this is A. Okay, and its normal direction is n cap, for example, or yeah, maybe n cap is any vector, uh, any unit vector. N cap is unit vector along normal. So this is the surface area. Now imagine that flux lines will go through this surface area. Sorry, magnetic field lines will go through this surface. Like this will go perpendicularly. Mm, Magnetic flux density V bar. So this is just an example. We will understand in deeply what is magnetic flux density, etc. Now, in order to calculate the flux here, we have to so we have to do the dot product between. Um, let's give this area as S cap, where S cap is A times N cap. Okay, so this is what we do for calculating flux. When we will do this is this B bar is this is first case, and second case another formula I am writing. Yes. Now the first case is when B bar is a uniform flux density, means all the flux lines that are coming out of this surface are equal in magnitude. So that means magnitude of B comma is magnitude of B is same of all surface, like magnitude of same of is same of all the flux lines. So this will applicable to this case. Now for the second case, B cap is non-uniform. So in the second case, what does that mean? So this flux line, for example, it may have different flux density value, and this might have another magnitude, different magnitude of magnetic flux density. So that's why we have two different. So here there is dot product. In both cases we do dot products, but how we are calculating that varies. Now let's calculate how to calculate the dot product of two vectors. So we have here A bar and B bar and theta. So now we may calculate, like, if we know the magnitudes and angle, then this is the formula, angle between them, and or else we may. So if the two vectors are given to us, then I cap, we may write x cap or I cap. we end up having dot product. Now here I cap and j cap, k cap, these are also these are also vectors. So let's understand what they are. Vector along x-axis, in fact unit vector. J cap is unit vector, k cap is unit vector along z axis. So also another thing now, along x-axis I cap, along y-axis k cap, or sorry, along y-axis it is j cap. K cap. Now the angle between any of these two is 90 degrees. 90 and this is also 90. So as it is 90, when we do dot product, between these two, 1 and 1 cos 90. So it is 0. Similarly, between j cap and k cap, dot product I cap is also 0. So when we multiply here and also I cap dot I cap is equal to 1 1 cos 0. Cos 0 is also 1, so this is 1. Hence it will be is equal to j dot product to 0. So now if we multiply uh, I cap dot product with the I cap, here we get 3 into 3, 9 combinations of um, dot products. So I cap dot product I cap is 1. So A bar AY BY AZ BZ. Now if we multiply a vector, if we do dot product between a vector A bar and itself, so this will give magnitude of A times magnitude of A. Angle between them is 0, so cos 0. Now next important thing is magnitude of a vector A bar along the along the direction of B bar. So in order to calculate that, we have to do dot product of A bar and unit vector along the direction of B bar. So here U cap. So what is U cap? It is unit vector along this P vector. Let's say that there is a vector A bar which is I cap plus 2j cap minus k cap, and we have a vector b bar which is I cap plus j cap plus k cap. Now we have to find the magnitude of vector A or along the direction of B bar. So that magnitude I'm writing like this along B. This will be is equal to 3 I cap plus plus 2j cap minus, and dot product with the unit vector. So in order to get the unit vector uh, along the direction of B, here unit vector B, how we can calculate unit vector B is nothing but vector B divided by its magnitude of the vector B. So magnitude of the vector B is calculated like this, and this is the vector B. So when we do the dot product, will be 3 times I plus 2j is and minus n plus 1 is by root 3. So 3 to 5 minus 1 is 4 by root 3. This is how we calculate the magnitude of a vector along this direction b bar. The dot product next. Now let's see about cross product. So when we are going for the cross product, we go for the cross product, then the effect due to two quantities give in a direction perpendicular to uh, those two vectors. For example, consider a plane. Okay, so it's easy to think like this. Or let's say that this is a plane. Two vectors are like this in a plane. Okay. Suppose let's say this A bar and B bar. Now these two vectors, not forces, sorry, these two vectors are giving the effect in a direction perpendicular to this plane. So let's say um, n cap is perpendicular to both A bar, comma B bar. So it is perpendicular to both A bar and the effect is due to effect is along effect um, will come along n cap, or it is supposed to come along n cap. In that case, we use cross product. Now, this will be is equal to magnitude, sorry, magnitude and sine theta. This is the angle theta. So this is the magnitude, and n cap is the direction multiplied with the unit vectors. So n cap is nothing but unit vector perpendicular to both a bar and b bar. Effect will come along this unit vector n cap, which is actually normal to the plane containing um, a bar and b bar. So actually, it is giving us, it is mathematically equal to area of a parallelogram. If we take a parallelogram like this with angle theta, so here this um, b is nothing but magnitude of the vector b and magnitude of vector a. If you find this area, it will be this area equal to and the angle between the two sides sine theta. For a rectangle, theta is 90. Rectangle is also a parallelogram with angle theta 90. There you get magnitude of A multiplied with magnitude of B. So this is when we know the magnitudes and the angle between them. Now when we are given two vectors, for example, as in the previous case, x I cap, we may use I cap or x cap to represent unit vector along x axis. Sorry, using J cap. In order to calculate A bar cos B bar. So this will come out as a vector. You have to find the determinant of this Ax, Ay, Bz. So this will be equal to the expansion I Ay Bz minus By minus J cap. These are unit vectors. Here J cap, so we get Ax Bz minus Bx. Then the continuation plus K cap Ax By minus Bx. So this is how we calculate the cross product of two vectors. So as I said, when we are using this, when the effect will be in the direction perpendicular to both vectors. So for example, this is a conductor, straight conductor having length L, um, and its unit vector, for example, in L cap direction. Let's assume L cap is unit vector of this, and it is carrying current I. So magnitude of the current that is carrying is I. Now it is in the magnetic field. This wire is placed in the magnetic field, magnetic flux density P cap. Okay. Now, when it is placed in the magnetic field B P bar, so the conductor will experience the force. So the force which it experiences will be perpendicular to this current direction and the magnetic flux density direction. It will be perpendicular. Effect will be perpendicular to both. That's the reason we do the cross product. So the cross product here will be I current magnitude, which is the magnitude of current, and length of the conductor here. L cap is the direction uh, through which the it is a unit vector along which the current is flowing, and we do cross product with E bar. So when we do that, we will get the force C. So this is the first part of the basics that we need to understand. In the next lecture, we will see in detail about cylindrical coordinates. So cylindrical coordinates will be clear in the next lecture completely. We will try to explore more comprehensively so that because we have different coordinates, Cartesian, cylindrical, and spherical coordinates. So using it will be suitable to choose each one of these coordinates for a that specific case. For example, a current carrying conductor, if it is there, sometimes it might be very easy to solve the problems using the cylindrical coordinates. Even the textbooks and everyone who teaches, they will use the cylindrical coordinates, and so for that particular case. So uh, it is necessary to understand these cylindrical coordinates in detail. Similarly, the spherical coordinates also we will see in detail. Thank you so much for watching, and please subscribe so that you will get standard NEAT and MCQ and MSQ just like in GATE. Those questions will be presented to you as we go along. Thank you.